What's up, folks? Welcome to the first lecture in Relativity, where we actually have a budget. Alright, so today we're going to be exploring the concepts of the Lorentz transformation. First, we're going to tackle the theory, and then we're going to try to involve some interactive visualizations that help you understand the concepts of length contraction and time dilation. So there's a lot of beautiful ideas out there. Let's go ahead and get started with some ideas. Okay, let's go ahead with the theory. By the way, this is the board we'll be using today. Okay. Let's first make this a blackboard. I'm not a big fan of whiteboards, even though I've been using them for the last 12 years. Let's go ahead and switch to a blackboard real quick, yeah? So here's my blackboard, and I'm going to start with two axes. And these two axes are going to be what? My position and time axes. So here's my time axis. I'm going to measure it in light seconds. That's why I have CT. And here is my position axis, which I'll just label X. Okay, so there you go. There is my first there's my two axes. Okay, now what we have right here is a space-time diagram. Any good space-time diagram needs to really have three things, or it can have three things, I should rather say. Okay, what are those three things? Well, first and foremost, you could have events. Okay, events are really things that happen. An event could be switching on a flashlight. It could be a supernova. It could be a star dying or a black hole collapsing or forming. Okay, so that's number one. You can have events. You can also have whirl lines. Whirl lines, whirl lines, whirl lines. Whirl lines are the path. They're the path of a moving object. They're the trajectory of a moving object in space-time. Okay, so for example, if you have a constant velocity object, their whirl line is just going to be constant throughout position, moving just through time. On the other hand, if you have if you have an object at rest, it's only going to be moving through time and not through space. If you have a constant velocity object with a non-zero velocity, it's going to have some kind of a linear whirl line, just like that, or even that. And finally, if you have an object that's accelerating in space, you're going to have a kind of a curved whirl line, something like this kind of a spherical guy that I just drew, or that. So those are just some examples of whirl lines you could have. Now remember, right here we've got a two-dimensional space-time diagram. Now, when you say two-dimensional space-time diagram, what you're really saying is you have a 1 + 1 dimensional space-time diagram. That means you have one dimension of space and one dimension of time. I could choose to have, instead of a 1 + 1 dimension space-time diagram, I could have a 2 + 1 space-time diagram with two dimensions of space, such as xy, and one dimension of time, such as ct. This would be a 2 + 1 dimension space-time diagram. Two dimensions of space and one dimension of time. But we want to keep things simple. We want to keep things straight. And a 1 + 1 space-time diagram is good for doing just that. So you can have events, you can have whirl lines. The final thing you can have are something called linked events. Linked events. Now these guys are very nice. Linked events are kind of phenomenon we're going to observe later on as we go into more advanced paradoxes that occur in special relativity. Paradoxes such as the twin paradox and all that good stuff. But those are really the three kind of pillars. Those are the three things you can have in a space-time diagram. Okay, so let's get to it. Let's first investigate an event. Okay, we're going to take a look at an event and perhaps how we can transform that event between two reference frames. So let me go ahead and erase all this good stuff, and we'll be good to go. We will be good to go. So let's erase all this. Bye to the space-time whirl lines and all of that. The good thing about these smart boards is you always know just how much to erase. Okay, so that is gone. Let's start with an event in space-time. Our event will be called E, and I'm going to place my event right here. It's going to be a yellow event, and it's going to be right here. Hopefully everyone can see my event. Okay, that right there is my event, and let's call my event E. Now, my event is obviously going to have some coordinates in space-time, right? It's going to have some coordinates. It's going to have an x coordinate. Whoops, that is one fat x coordinate. So you're going to have an x coordinate. Let's call that x naught. You're going to have a time coordinate. Let's call that t naught. All right, so the position of this event E in the reference frame of observer A is simply going to be x naught comma t naught. One thing you should note, by the way, is that if an observer's world line is simply simply their y-axis as such, then the world line, or rather the space-time diagram you're looking at, is from that observer's perspective. So for example, if Timmy is moving 10 meters per second through space, through one-dimensional space, at a constant velocity, and we saw that his space-time diagram was just a straight line, just a vertical line like that, just the time axis, then we know that the space-time diagram we're looking at is from Timmy's perspective. Okay, it's from Timmy's perspective. So we have our event E, we have x naught t naught. We basically have everything we need. Now, this is basically the end of our lecture today, but let me just give you a preview of what we're going to be looking at in the future. If we want to look at the coordinates of event E for another observer, let's say event E is a new restaurant opening up. You got your old friend Bobby on the phone and you tell him, Bobby, as soon as that restaurant opens up, I want you to meet me up at that restaurant. Now, Bobby's going to try to meet you up at the restaurant at the same place at the same time. But it's not that easy. It's not that easy. Why? Why is it not that easy for Bobby to meet you where you want him to meet? Is Bobby just being a rebel? No. Because this is some intergalactic restaurant. Let's say here is our restaurant. We'll call it restaurant R. And here is Bobby. Bobby's right here. Oh, that's not Bobby. Bobby's gonna be, I don't know, Bobby's gonna be in the bronze Bobby. Okay, that's Bobby right there. The yellow dot represents Bobby's position. Okay, this is where Bobby starts out. And of course, we have Timmy as well, right? We got Timmy. Or why don't we just use Rifat? That's me. So we got Timmy and Bobby, or Rifat and Bobby, okay? So Rifat is going to be right here, and Bobby is going to be right there. Now here's the thing. Bobby and Rifat are both moving at a certain constant velocity. Let's say Bobby's moving at a constant velocity of, I don't know, 5 meters per second. Okay, and let's make that nicer. Bobby's moving at, for example, 5 meters per second, and Rifat could be moving at a slightly higher velocity, maybe, I don't know, 7 meters per second. Okay, now maybe just through one-dimensional space-time, just horizontally, like that. Okay, so Bobby's moving through space-time at a constant velocity of 5 meters per second in just the horizontal direction. Rifat's moving in the same direction, 7 meters per second, once again in constant velocity and the same direction in just the horizontal direction, okay? Now, the restaurant they want to meet up at, restaurant, let's call it restaurant intergalactic, okay? Let's call it restaurant I. The intergalactic restaurant. Sounds pretty cool. Now, Rifat and Bobby want to meet up at the same time. As soon as the restaurant opens for its opening date, they want to be there at the same time, at the same spot, at the intergalactic restaurant. Can they make it happen? Well, it's going to be incredibly difficult, or at least without Einsteinian relativity, it's going to be incredibly difficult. Okay, why is that? Well, it's simply because Bobby and Rifat are moving at different velocities, right? So what Rifat may perceive to be the coordinate of this event I, Rifat might think that the space-time coordinate of this event I, this restaurant opening up, might be x naught t naught. Or you know what, let's keep things even simpler. Rifat might think the space-time position coordinates of this event I is going to be x comma t. Whereas for Bobby, these are completely different coordinates. These are x prime and t prime. And x prime and x are not equal. T prime and t are not equal. But to transition from x prime to x and from t prime to t, we're going to need a set of transformations to transition between these two guys, to transition from these two guys, to make sure that Rifat and Bobby can indeed meet up, to ensure that these guys can indeed meet up at their preferred destination. We need a set of transformations that can go from Rifat's coordinates to Bobby's and from Bobby's coordinates to Rifat. And what is that set of transformations? Well, it's the very set of transformations that Hendrik Lorentz derived and that Einstein himself derived after proposing the two postulates of special relativity. And that, ladies and gentlemen, is why we need the Lorentz transformation. Lorentz transformation. Alright folks, that's it for this lecture on special relativity, and we'll check you out next time.
Ambition plus MKO plus scaffolding equal learning. We believe anyone can learn anything. That's why our motto is memorization is a crime. And that's why we partnered with Brilliant.
Brilliant transforms math and science into hands-on activities so that you too can understand everything from first grade math to E equals MC squared. Barry Science Lab and Brilliant is your MKO and will give you the scaffolding to expand your ZPD until you become the next Sir Isaac Newton or Albert Einstein.
Visit brilliant.org/Barry Science Lab today. And the first 50 of you to use that link will get a 20% discount on the Brilliant annual subscription.
Don't forget that you too can become the next Einstein. So let's fall in love with math and science.